I mentioned briefly in an earlier video that the rate constant is only a constant at constant temperature, or I may have just said temperature dependent, but the rate constant does change with temperature. The Arrhenius equation is an equation that will let us calculate the rate constant. What we typically end up doing is getting the rate constant from method of initial rates data and then using that data, especially at different temperatures, to calculate the activation energy, which is one of the components in here, and the frequency factor. So in this equation, lowercase fancy k equals a e to the negative ea over rt. The k is the rate constant. A is this thing called frequency factor, which I'll go into what the frequency factor means in a little bit. The EA is the activation energy. So we'll draw a picture that will make this a little bit easier to see. The activation energy is essentially just the barrier that you have to get over to get the reaction going. R is the gas constant, but now it's the 8.314 version because we need something that will cancel units, which, by the way, remember that this is in joules per mole Kelvin. So when you get an activation energy out of this, it's going to be in joules. And if you're putting an activation energy in, it has to be in joules or you have to convert R to kilojoules. And then T is the temperature in Kelvin. So official definitions, the activation energy barrier that must be overcome to turn reactants into products. And the graphical depiction that we can show of this is an energy diagram. And it just shows the energy changes in a reaction. So we are going to plot energy over the progress of the reaction. Now, this is sometimes labeled RC for reaction coordinate. What that really just means is that reactants are on the left and products are on the right. And I have one elementary step shown in this picture. Not every reaction is one elementary step. We might have several like bumps that look like this to show an energy diagram for the course of a more complicated reaction. And it would still go, the beginning is on the left, and then we keep going to the right until the reaction has completed. So on this diagram, our y-axis is energy, and I don't have any references here, but remember, these are all negative values. We're all below 0 on this scale. And what it plots is the reactants. So that energy that's listed usually is going to be something like a delta H or a delta G that just represents the reactants. And then the products, I have that over on the right. I've got a line just for the energy of the products. Again, delta G or delta H. And the difference between those two is the delta H reaction or the delta G reaction, depending on which you have plotted. So regardless, this also helps to show that delta H is a state function, that delta G is a state function. It doesn't matter what the actual plot looks like going from reactants to products. I just need to know the beginning and the end, and I can have my delta H. So my curvy, bumpy line is going to show that my reactants, I have to go, whatever happens, I have to go up in energy, and then I can go down in energy to get to my products. Now, the step that I have shown here, my products are at a lower energy than my reactants, which if you remember way back, this means that the reaction is exothermic. They're not all exothermic, which we have shown several times, so it's also possible that the products could be at a higher energy than the reactants. So on this, right, I have this barrier, this energy barrier that I need to overcome. So from the reactant energy to the top of this peak, that is the activation energy. So that amount of energy that I need to overcome. I have my delta H labeled, and then there's also a special name at the very top of this peak. There's a high energy state called a transition state. And transition states are super important for what your products look like. You'll spend a lot of time thinking about transition states in organic chemistry as you're coming up with products to your reactions or figuring out which product is more likely, or just where things go when you make a product. So that's what this spot is called. It's not something that can be isolated, but it is something that we have found ways to observe and is important to creating your products in your reaction. Okay, so finding the activation energy and the frequency factor. Both of them depend on the reaction that's being studied. The way that we do this is we determine the rate constant at various temperatures, and then you can make an Arrhenius plot, or, right, this is going to look really familiar. You can do a single point form or a 2-point form. The Arrhenius plot would be the single point form. This is a plot of the natural log of the rate constant versus 1 over T in Kelvin. And it gives you a straight line that has the equation natural log of K, which is Y, equals negative activation energy over R, which is your slope. 1 over T is your X component, plus the natural log of A, which would be your intercept. So from the intercept, you could find the frequency factor, and from the slope, you could find the activation energy. There's also the 2-point form, which if you know the rate constant at one temperature, you could find the rate constant at a different temperature, or you could find the activation energy if you know the rate constants at 2 different temperatures. Now, obviously, this leaves out the frequency factor. So if you needed to find the frequency factor, you would find the activation energy and then choose one point and plug it back into the straight line plot, that single point form, because it's the only version that has our activation energy. Or you could plug it into the initial Arrhenius equation, the K equals AE to the negative EA over RT, and find the frequency factor that way. So the collision model tells us about the frequency factor. So why is there a frequency factor and what does it mean? So now that you've seen the energy diagram, we have this energy barrier that we have to get over, and the frequency factor is a measure of how many times the reaction tries to get over the barrier per unit time. So essentially, every time the reactants come together or do whatever they need to do to move toward product, not every approach has enough energy to overcome the barrier. And the molecules have to run into each other with the proper orientation. And I'll draw a picture to show, or I'll draw some structures to show what this means. So the kind of overall is that the reaction occurs after a sufficiently energetic, properly oriented collision. So things need to line up and they need to have enough energy when they approach the barrier. The frequency factor represents how many times they might do that per unit time. So proper orientation, the reaction I want to look at is 2NOCl turning into 2NO-NCl2. So if I have my NOCl molecules, these aren't proper structures. I haven't filled in all of my bonds or put in my lone pairs, but it's a nice skeleton with the correct connectivity. If I have these two molecules and they run into each other with this orientation, the things that I'm trying to make, NO and Cl2, I mean, maybe I could make NO from this, but I'm trying to make Cl2. So my Cls need to connect to each other, so they need to run into each other. So this kind of collision would not be effective, and this would represent one of those approaches to the barrier that's unsuccessful because the molecules don't line up. If they line up to form Cl2, this is how you might get an effective collision. So the Cls run into each other, they can form Cl2, the oxygen chlorine bonds could break, and you're left with the two NOs that you need. All right, so another picture, just a better maybe representation of what's going on in the frequency factor. And this is, right, I've got my energy diagram going from reactants to products. This time I've got an endothermic reaction shown. I've got my activation energy labeled, and the frequency factor is in the calculation for the rate constant because it affects the rate of the reaction. So again, what we're showing is that the reactants attempt to overcome the activation energy barrier, and right, it's unsuccessful. And then we have another approach or attempt, and maybe it almost has enough energy, but then they're not lined up right, so that doesn't work. And then we have another approach, and then maybe this one doesn't have enough energy, so it doesn't work. And this keeps happening until you finally have enough energy and the correct orientation to get over that barrier. Now, the more times you try to go over the barrier unsuccessfully, the longer it will take for it to go. So this is why the frequency factor is built into that calculation.